Hi everyone, thanks for joining us. We are Autonomous Vehiculum. In the next few minutes, we'll show how simple, consistent visuals made our AV operation easier to read and how that clarity led to specific changes on the airport express route. We're going to look through four lenses: reliability, energy, safety, and passenger sentiment using a 5-week daily dataset across three Toronto routes: downtown loop, Airport Express, and University Shuttle. Here's the promise: you'll see a before and after around one decision, and we'll end with three concrete actions and a short roadmap so this does not stay as nice charts. It becomes operational change. Everything you'll see is reproducible from our Python notebook. We export images to keep scales and colors consistent. Moving forward to the next slide, which is executive summary. So here's the headline. 1. During heavy rain, on-time performance on Airport Express fell by roughly 5 to 7 percentage points compared with clear or cloudy days. 2. The visuals that actually changed the decision were single-story chats with short annotations, not dashboard scrams with tiny plots. 3. After we added rain window buffers and reordered two stops to reduce left-turn conflicts, we saw about a plus 3-point lift in on time in the next rainy weeks, and hard brake incidents eased. We'll walk the evidence, the actions, and the expected impact for the next 4 to 6 weeks, and we'll be careful about correlation versus causation. We use the same scales next month, so comparisons stay honest. If anyone wants exact days or deltas later, we have a small numbers pack with rainy was a clear comparison, and the 5 worst are 2 days. Moving forward to the next slide, stakeholder goal. Our stakeholder goal was speed and clarity. Make performance and risk obvious in under 2 minutes for a busy reviewer. So we enforced one rule, one chart, one story. If you want another angle, you slice it by route or weather instead of stacking three metrics on one axis. Our deliverables are exactly what you asked for: a PowerPoint deck and a short screen recorded walkthrough. Longer term, we will experiment with light interactivity over tooltips and filters, but today is about crisp slice, standardized access, and clean narrative. Standardizing access sounds small, but it kills the subtle trap of moving baselines. Your eye reads change, not absolute scale, so we lock scales to prevent misreads. So, the next slide will be data and scope. Build trust, what you measured, why, synthetic but realistic. We used a 5-week daily dataset for three routes: R1 Downtown Loop, R2 Airport Express, R3 University Shuttle. Per route day we track on time rate, energy, and Regen percent, incidents split into hard break and near miss, a severity index, and passenger sentiment via CSAT 1 to 5 and NPS -100 to +100 with weather tags. It's synthetic but realistic. Relationships match what ops teams actually see in rain. On-time dips, energy climb, safety indicator spike. We use daily granularity to avoid noise. We clip impossible outliers and keep definitions tight. Every chart is reproducible from the notebook and exported as PNG, so labeling and colors are consistent slide to slide. We also normalize safety as incidents per 1,000 trips, so demand spikes don't fake a trend. More trips can mean more incidents even if rate is steady. So the next slide will be KPI frameworks, with the goal will be map metrics to leader questions, give anchors and levers. To keep decision clean, we group KPIs by leader questions. Reliability, on-time rate equals on-time trips divided by total trips. This is North Star for trust and future demand. Our working threshold is greater than equal to 90%. Dips get attention. Second, cost or efficiency. Energy, which is a kilowatt hour per day, and regen percent. Baseline energy per trip sits around the mid-teens. In rain, we expect a bump from stop and go and HVAC. Levers are smooth brake, and brake smoother braking, charging strategy, and buffer decision. Safety, heartbreak plus near miss counts and severity average 1 to 5. These are leading indicators. We act before crashes. The lever is conflict reduction, for example, left turn exposure and operator coaching. Passenger, CSAT 1 to 5 and NPS from negative 100 to positive 100. CSAT moves with comfort, NPS moves with perceived reliability. The lever is predictability, arrivals that feel on time. Separating these avoids mixed scales, keep each slide story obvious, and links KPIs to specific operational levers. Think of it as North Star leads to drivers, leads to levers. On time is the North Star, drivers are weather and conflicts, levers are buffers and star power. So what's the executive want? So in conversation with stakeholder, three requests were consistent. First, give me one chart I can slice, not 20 tiny variants. So we design one story per slide and make the sliced out or whether not another micro chart. Second, standardized X's and short callouts beat fancy palettes. We annotate the three key moments directly on the line, worst tip intervention, and next 20 weeks so the cause and effect is skimmable. Third, keep a weekly live view for operations but produce a monthly deck with 3 screenshots executives can scan. We also include a single line method note, for example, how incidents are counted because transparency increases trust. That's the approach you'll see next. A simple trend, 2 to 3 annotations, and when we needed, a slice. So Shihana will start with reliability and energy and show how the rain pattern on Airport Express justified the change. Over to you, Shihana.
Thank you, Rohit. Now, let me ground this in one concrete example from Route 2. On this slide, you see a simple overlay, R2's on-time rate and a rain indicator, plus 3 callouts. Every time rain spikes, R2's on-time rate drops. On clearer days, it recovers. The pattern repeats. The callouts show a heavy rain where R2 falls below our acceptable band. The change we made right after, small time buffers on key windows and a reordered stop sequence in a congested area. The rainy days after that change, where R2 still reacts to weather, but the dip is much smaller. The point of leadership. We didn't ask for more buses or a redesign of the network. We used data to justify small low cost changes that are easy to approve. This sets up the next slides. We'll show how those tweaks appear in reliability, how we make weather actionable, and what it does to energy use. Now, zoom out to one time performance across all three routes. This chart shows daily on time rate for R1, R2, and R3. One metric on the y axis, days on the x axis, 3 lines, and a short legend. The story is clear. R1 and R3 are relatively stable. R2 has several sharp dips. We have highlighted 3 worst drops. Each lines up with heavy rain that tell us the problem is concentrated on R2 and it's strongly tied to weather, not random operations. After we introduce the buffers and change stop order, the later rainy periods still move, but the dips are shallower. R2 doesn't crash the way it did before. So for X's, the slide answers what's the issue? It's an R2. And what drives it? Well, it's rain. Did the fix matter? Yes, of course. Post change dips are less severe. We keep this chart clean on purpose. No extra KPIs. It's a single story, reliability by route, before and after we act. Here we show how weather becomes an actual decision input, not just a complaint. We take R2's reliability curve and heavy rain callouts directly on the chart. Those bands show exactly where drivers are dealing with reduced visibility and slower traffic. From that, The decision is simple. Add rain buffers on the most vulnerable R2 windows, especially around left turn clusters and known congestion points. When those rain beds are active, R2 runs with buffer. When they are not, we tighten back. Yes, buffers make extremely clear days slightly more conservative, but they pretend the schedule from collapsing on bad days. We manage that trade off by reviewing and tuning the buffers seasonally, not locking them in forever. So, this slide proves we are not just saying rain hurts us, we are showing where it hits and where we insert buffers to control it. Finally, let's move to the cost side, which is energy. This chart shows daily kilowatts by route R1, R2, and R3. Look at R2 here. You see energy spikes, more stop and go, more abrupt braking and concentration, higher HVAC load. So when rain hits, R2 become both less reliable and more expensive. After the buffers and small routing tweaks, we are promising a flat line, but on comparable rainy days, we want smoother driving, slightly lower daily kilowatts per hour on R2. We compare pre-change versus post-change rainy periods, and we use R1 and R3 as a control. Reliability and energy together explain the why behind the buffers. We are not padding schedules just to feel safe. We are trading a small planned buffer in concentrated conditions for fewer late trips, less driver stress, and lower wasted energy. So, to close this section, I would say Route 2 showed us that weather is a predictable stressor, not a surprise. By overlaying rain, on time performance, and energy, we turn that stress into a design input, targeted buffers, and a minor routing changes that are cheap, controlled, and measurable. With that foundation on performance and cost, Onamaya will now walk you through the third lens, which is safety and passenger experience. Thank you.
Hi, I'll be discussing about these points now. So the first one is safety incidents over time, and the second one is safety details, severity, leading indicators, and we have passenger CSAT trend and passenger NPS trend, and finally we have efficiency regenerative braking. So let's see the first one, which is safety incident over time. So this chart shows our safety incidents over time broken down into two major categories, which is hard breaks and never misses. Presenting it as a stacked chart helps us to understand not only the total volume but also the mix of incident type. So when we separate the data like this, a clear pattern appears. During rainy periods, both types of incidents increases, but heartbreak incidents rise faster. This that's expected because wet roads affect stopping distances, which increases the likelihood of the abrupt braking. But they key insight that what happens after the route adjustments were introduced. We see a consistent downward trend in total incidents. What is important is that we normalize the data to reflect incidents per 100 trips. This ensures our analysis remains accurate even when the trip volume fluctuates, for example, on weekends or on during the peak commuter hours. By keeping this stacked chart, we preserve visibility into the type split while still focusing on the overall trend. In simple terms, that this helps us to understand now just how many incidents happened, but what kind and why. This gives us a clear picture of operational risk and makes our improvement story easier to communicate. So next we have the safety detail. Severity leading indicators. Along with this incident counts, we track the average severity of those incidents. Even if incident numbers stay the same, an increase in severity can indicate growing risk. For instance, for instance, a heartbreak at high speed creates high jerk, so which passengers immediately feel. So severity become a very meaningful metric. What we found is that even a small drops in heartbreak incidents leads to noticeable reduction in braking in average jerk. This connects directly to passenger comforts and overall safety protection. So we treat heartbreak frequency as a leading indicator. This means that if we see a sudden rise in heartbreaking even before severity changes, we know that there is something happening on the road that requires attention. So when we spot outliers such as spike on single segment of a route, it automatically triggers a review. The operations team looks at these things like map geometry, lane width changes, signage, dwell times, and the temporary any temporary road work. So this proactive approach lets us intervene before the severity trend begins drifting upward. So this slide is really about how we don't wait for a major event. We act early by monitoring high sensitivity signal. Next we have the passenger CSAT trend. Passenger satisfaction tells how operational decisions appear from customers' perspective. In this trend, we can see a dip that aligns perfectly with the rainy weather windows showing earlier in the safety slide. This reinforces something important. When the environments get more challenging, overall ride experiences become impacted. But what's encouraging is that the rebound after the route and the operational changes were implemented. The movement in CSAT may look small at first, increasing by zero point 0.1 to zero point 0.2 points, but at scale, these are highly meaningful improvements. So even slight lift represents hundreds of positive experiences across riders. The consistent story what we wanted to highlight is that fewer abrupt stops plus more predictive arrivals is equal to a smoother and a safer passenger experience. So this trend reassures us that the changes we made weren't just operationally efficient but also the customer visible. When passengers feel safer and more comfortable, their satisfaction naturally increases. So next we have passenger NPS trend. NPS focuses less on moment to moment satisfaction and more on passenger perception of reliability, trust in the service. When we look at the NPS trends here, we see a modest but steady increase after our operational change. This tells us that the rider are not only experiencing better trips, but they are also feeling more confident in recommending the service to others. Reliability in particular plays a huge role in NPS, and when sudden stops are unpredictable delays decreases, the overall perception of reliability strengthens. Going forward, we are planning to enrich this view by adding shorter rider comments and categorizing the reasons for positive and negative scores. So this will help us connect the trends with actual passengers' voice, making it easier to understand why sentiment is shifting. The big takeaway here is that the improvements in safety and comfort are clearly visible to passengers and they are expressing it through higher recommendation scores. Finally, we have the efficiency regenerative braking. Now let's look at how the safety and comfort improvements affects the energy efficiency. Regenerative braking works by best during smooth controlled deceleration and the same type of braking that passengers find comfortable. Interestingly, regen percentages tend to rise in rainy periods because there are more braking events overall. However, with good coaching and route design, heavy braking can increase jerk, making the ride uncomfortable. So, our aim is to maintain or increase the regen percentage while keeping jerk within comfort thresholds. This balance is important because it ties together several goals, which is nothing but energy recovery, smooth deceleration, safety, and passenger comfort. So, coaching operators to brake earlier and more gently preserve the regenerative benefits and avoid harsh stops. This helps lower energy costs per trip without compromising the customer experiences. So this slide helps us to close the loop between safety, comfort and operational efficiency, showing how improvements in one area can benefit across the entire system.
Route Spotlight. Now I want to spotlight Route 2, the Airport Express, because it gives us some of the clearest, most actionable insights in this entire analysis. R2 had two unique characteristics that made it especially sensitive to weather disruptions. First, Airport Express riders are typically the most sensitive customers. They're often catching flights, making connections, or operating on tighter schedules. So, even small delays on this route hurt passenger satisfaction more visibly than on common routes. Second, among all our routes, R2 showed the strongest rain related performance drop. During rainy weeks, we saw noticeable dips in on time performance, and we also saw a spike in operational incidents. Things like harder braking and conflict points at busy intersections. What's interesting is that we didn't need complex interventions to fix this. Instead, we introduced two very low cost operational changes. Minor dwell buffers during predictable rain windows being one. These weren't fully scheduled changes, just small cushions added selectively so operators weren't pressured during weather slowdowns. And the second was stop reordering to remove left turn conflicts. This is a tiny routing tweak, but left turns are one of the biggest contributors to delay during rain because visibility drops and turning speed slow downs dramatically. The result of these two small changes was a roughly 3-point lift in on-time performance during rainy weeks and a measurable reduction in daily driving incidents. This is a great example of how micro adjustments guided by data can outperform big expensive system-wide changes. Moving on to the next slide, based on what we learned from R2, we have three intermediate action items that we are continuing to execute. First, we are keeping those rain buffers, especially during R2's peak travel windows. These are the windows where the data shows the highest vulnerability, so we want stability there. And we'll start testing similar micro buffers on route R1 if we see the same weather-driven patterns emerging in the next few weeks. The second is we're maintaining the stop order adjustment. The new sequence that removes the left turn conflict is showing very clear benefits: fewer hesitation delays, smoother curves, and less operator stress. Since this change doesn't affect the passenger experience at all, it's an easy win that we want to retain. And the third is we'll continue operator coaching focused on smooth deceleration and regenerative braking. This isn't about micromanaging drivers, it's about reducing unnecessary spikes in speed and motion during variable weather. Smoother deceleration not only cuts incidents but also improves energy efficiency. These three actions are already in place and they're all low cost, low disruption improvements that build directly off what the data told us. Moving on to the next slide, impact projection. Looking ahead to the next 4 to 6 weeks, here's what we expect if we keep these interventions in place. 1. On-time performance should improve 2 to 4 points during rainy weeks. We're already seeing early signs of this, and the reason we give a range is because rainfall intensity varies week to week. But regardless, the direction is firmly positive. 2. Daily incidents should drop 10 to 15% per 1,000 trips. The combination of smoother deceleration, reduced turning conflict, and slightly eased timing pressure leads operators to drive more predictably even when visibility is lower. 3. The energy usage should decrease 3 to 5% per day. That does not sound huge on paper, but across a full route or monthly cycle, this translates into significant operational savings. The smoother profiles help the regenerative braking system work more effectively, and fewer harsh maneuvers reduce battery stress on electric fleets. A key point here is that we will validate all of this using the same charts, same measurement windows, and same definitions that we used before. This ensures we can make an honest apples to apples comparison, and it avoids the common problem in analytics where KPIs shift halfway through an improvement cycle. Risk and trade-off. Of course, no operational change is risk-free. So here are the trade-offs we are monitoring. First, rain buffers can increase cycle times on clear days. By adding even a small cushion during peak windows, we risk slightly lengthening the overall route if the weather stays dry. To manage this, we are reviewing buffer sizes on a seasonal basis to avoid overpadding. Second, the operator coaching must be balanced. Too much coaching can make drivers feel overly controlled, which can lower morale and reduce responsiveness during unexpected situations. The goal is to guide behavior and not script it. And the third is data definitions must stay consistent. If definitions change, such as how we classify incidents or how we calculate on-time performance, it becomes impossible to tell whether the improvement is real or just a measurement change. So we've put in place consistency checks to ensure everything we track remains aligned. These trade-offs are manageable, but it's important to call them out so our improvements don't accidentally create new problems elsewhere. What we'll improve next? For the next iteration of the dashboard and this analysis, we want to make a new light high value improvements. First, we'll add small KPI cards directly on the reliability slide. These will highlight the week's on-time rate, incident rate, and energy usage in a clean, simple one-look format. Second, we'll visually annotate rain windows directly onto the charts. This makes it easier to spot correlations without needing to jump between separate graphs or data tables. Third, to add a bit of human context, we'll include one rider quote per month. Nothing overwhelming, just a single perspective comment that captures sentiment. This keeps us grounded in passenger experience without cluttering the analytics. The key principle is to add clarity and not complexity. These small touches will make our next round of analysis even more intuitive. The key takeaways from this presentation is some of the most important lessons from this section we just pointed out. First, one chart with one story is always better than many charts with mixed signals. Where the story is clear, decisions are faster. Second, the rain is predictable. So instead of reacting to it, we should plan for it. Micro-scheduling and routing adjustments aligned with rain windows give us consistent wins. And the third is small targeted operational changes create measurable improvements. We don't need full route redesigns or major investments. Sometimes the biggest performance gains come from tiny tweaks informed by real-world data. When we combine these ideas, simple insights, predictable patterns, and small operational nudges, we unlock a lot of reliability, safety, and passenger satisfaction improvements and very minimal cost. Before closing, here's a quick overview of the methodology used in this analysis to ground our findings. We worked with a synthetic daily data set representing 3 routes over 5 weeks. This allowed us to test patterns consistently without worrying about any missing data or incomplete logs. All the visuals you saw today were created in Python and exported as PNG images for this deck. This ensures reproducibility and makes it simple to iterate as the data evolves. Thank you for your time. We are happy to share both the notebook and the slide deck for anyone who wants to explore the data in depth. We're also planning to post a short video walkthrough that highlights the key callouts on the reliability and safety slides, so stay tuned for that. If you have any questions or want to dive deeper into the methods or next steps, we'd love to discuss. Thank you.